Anna Rafferty from the Computer Science Department at Carleton College, and I'll be talking today about recognizing student strategies and misunderstandings using inverse planning. I'm super excited to be talking about this at an educational data science conference because there are so many fascinating kinds of educational data. The one that I'm particularly interested in this work is complex tasks where a student might need to take multiple actions to try to achieve a goal. For example, a student might be trying to figure out the pH of a particular solution in a virtual chemistry lab. She might take multiple actions, none of which are really right or wrong, unless they're interpreted in the context in which they're taken, and with thinking about the overall goal that the student is trying to achieve, they might allow us to give us insight into her strategies, as well as what information she understands and what she misunderstands about chemistry. I think that lots of educational data can be interpreted in this way of consisting of multiple actions and a student trying to achieve some goal or maximize some reward function, like in an educational game. And we might even think of algebraic equation solving as falling into the same pattern. We can ask a student to show her work, doing her step-by-step equations, and we can see not just is she mathematically correct or incorrect at each point, but we might want to interpret what ways is she correct or incorrect, and what's her overall strategy for getting from an unsolved equation to a solved equation. So my goal in this work is to try to make fine-grained inferences about what a student understands and what she misunderstands, as well as possibly about her goals and strategy, based on data from these kinds of environments. And I'll be taking a computational modeling approach. In this approach, we'll try to have models about the domain content that the student is working with, as well as the game or task that she's working within, models about how knowledge is represented and how that's likely to change over time, and a relationship between these models and the data that we actually observe. In particular, I'm going to be interested in trying to formally characterize behavior in these complex tasks in order to find approaches that are modular and generalizable. We can kind of state how all the variables are related to one another and then try to make inferences about those that we don't get to observe directly, like what a student understands and what she misunderstands. I'll draw on approaches from machine learning and statistics where we can use some sophisticated modeling approaches that apply to lots of different situations. That's kind of one of the benefits of formally characterizing the behavior. And also having a goal of sometimes developing methods that might be applicable back in other contexts of machine learning based on the specific nature of the educational data we're working with. So let's take a look at how this applies to interpreting behavior and inferring misunderstandings in these complex tasks. The framework that we developed we'll call Bayesian inverse planning, and it relies on drawing insights from inverse reinforcement learning. In inverse reinforcement learning, we assume there's some automated agent who's observing an expert's actions, say how they solve or how they pilot a helicopter in a particularly complex way. And the automated agent is going to assume that the expert is trying to maximize some reward function. There's some reason they're taking these actions. The automated agent tries to infer that unobserved reward function from the actions in order to allow it to take actions in a whole host of other situations and on its own. So to apply this to the problem of inferring student understandings and misunderstandings, we'll think of students as like those experts. We assume that they're trying to maximize rewards given what they know, but they might have some systematic misunderstandings. So rather than there being only an unobserved reward function, we might have that there's some unobserved beliefs about how an environment operates, and we're trying to make inference about that in an automated way. We might also have some knowledge of the reward function already based on the task specifications, but there might be ways that reward function is unspecified, that we may not know about a particular student, how much she values particular things, and again we'll try to infer that from the data using methods like inverse reinforcement learning. So in this talk, I'm going to flesh out that Bayesian inverse planning framework and then tell you about how we've used it to try to close the loop between analyzing student solutions to actually providing them with guidance. I'll then talk a little bit about some ways that we can leverage the modularity of inverse planning to apply it to new situations and talk a little bit about future directions. So Bayesian inverse planning is this framework that I said is inspired by inverse reinforcement learning. And to really understand it, I think we need to start off with what is the top level assessment goal? And what we're going to be trying to do is to infer a distribution over possible ways of understanding and or student goals given the observed behavior. So the idea is let's specify a space of possible understandings and goals where each thing in that space is a possible way that a student might understand or might misunderstand or possible things she might be trying to do. Then we're going to try to find a posterior distribution over that space given her observed behavior. The advantages of this kind of approach are that it will allow us to specify that theta at the right level of granularity for the inferences we'd like to make. So you can make it more fine-grained or a little bit more coarse. By having a posterior distribution, we can try to figure out not just what is the most likely understanding, but also how much does the evidence support that? Should we wait and collect some more information before we take any actions to respond to a particular misunderstanding? Or are we pretty certain, yeah, the student is taking this kind of suboptimal strategy, maybe we should try to intervene or change our pedagogical policy based on that? So I'm going to use as a running example through these first couple sections is about equation solving. So if we want to apply Bayesian inverse planning to equation solving, we'll need to specify a space of possible understandings about equation solving specifically, and then we'll be finding a posterior distribution over theta given the student's equations that she writes down as she's solving a particular equation. So to specify that space of possible understandings, we turn to existing literature about algebraic equation solving. I wouldn't claim that this is the most perfect representation of algebraic equation solving skills. Instead, this is one that seemed to work pretty well for the kinds of misunderstandings that we wanted to infer, and will serve as a guiding example. So we made theta the six-dimensional vector of parameters related to skill. 4 of them involve conceptual mal rules like combining unlike terms, one of which is about arithmetic skill, and one of which is about a student's ability to plan, kind of about her strategy for going from an unsolved equation to a solved equation. So to find this posterior distribution over theta, we'll break this down into the product of the prior and the likelihood. The prior will be used to encode information about what misunderstandings are common, something like maybe a sizable minority of 7th grade students tend to combine unlike terms. We'll draw on existing literature for that or use an uninformative prior if we don't have much information. The likelihood is the more challenging thing to calculate because it has to tell us what is the probability of the observed data if the learner has a particular understanding. So we need to figure out then this whole sequence of actions the student is taking the complex task. How probable is it that she would have produced that if one particular theta reflected her understanding or her goals? That means we need a generative model for action selection. And for that, we'll turn to Markov decision processes. So Markov decision processes are a common decision theoretic model for tasks where multiple actions must be taken over time and where there may be long-term consequences to those actions. That seems to fit exactly the kinds of tasks that we're thinking about. So to specify the Markov decision process, we have a set of possible states and actions. For equation solving, the states are the different possible equations. Actions are things like moving one term from one side to the other. And we have a reward model that gives us the incentive structure. What is the student trying to do, or what does she believe she's trying to do? What does she value? And then finally, a transition model for transformations. So this is what the student believes is going to happen based on the actions that she takes. In equation solving, since she's actually writing down the next equation, she actually has complete control over that. So it's how does she think this works? In something like an educational game, she might have a belief about what's going to happen that might or might not be consistent with what will actually happen. The way that we'll connect this up to that theta is to map from a theta to a particular MDP. And so that theta may impact any part of the underlying MDP, including the transition probabilities. Different understandings might mean that you believe that different things are going to happen. Characteristics of the action choices, the action set itself, the state representation, and things like the rewards, what is the student value, and so on. So for equation solving, we'll focus on transition probabilities, the action set, and the planning characteristics. So for example, if we take these different dimensions, for the conceptual mal rules, there were 4 dimensions of theta in there. 3 of those affect the transition probabilities in the MDP, and one of them is about the actions set. So a student who combines unlike terms has more possible actions to take than one who does not combine unlike terms. To put this all together, we need some way of relating the actions the student chooses to that theta. If she's always just choosing actions completely randomly, then her actions can't tell us anything about what she understands and what she misunderstands. There are multiple ways that one can define this. The way that we've typically taken in our work is to assume that students are choosing actions noisily optimally. So they tend to choose actions that have higher long-term values, but they don't do so perfectly. In our work on equation solving, we have this theta sub beta parameter, which is estimated for each student to tell us how optimally does the specific student choose her actions. That can give us a characteristic of how well does she plan out how to go from an unsolved equation to a solved one. So putting this all together, to give you the big picture of inverse planning, we represent understanding and goals in a particular domain using this space theta. We then have to model our task as a parameterized, potentially parameterized MDP, and then given a step-by-step sequence of data, we infer a posterior probability over that theta given using techniques like MCMC. So what does this look like? Here's the output for one learner in our equation solving experiments. The green lines show us the expected value of the distribution. Each plot has a marginal distribution from the MCMC samples for one of the dimensions. And we can see that in addition to that green line telling us that some dimensions the student seems to be closer to mastery than on others, we have these black histograms of samples that tell us about the amount of confidence we have in that estimate, giving us both those fine-grained inferences along particular areas of misunderstanding and some information about where we might need to collect more information. We've tested out in the lab and using some simulations to try to figure out how accurate this inverse planning is, finding that in simpler domains where people can easily report their understanding, we get good agreement between what people say and what the system infers. And in simulations with equation solving, we have pretty good correlations for 5 of the 6 parameters with what teachers say they think the students, how well they think the students are doing along each dimension. We've also applied this in other domains. So my work with collaborators Michelle Lamar and Tom Griffiths, we applied this to infer misunderstandings about cell biology. And there's been other work in which people have applied inverse planning to assess inquiry skills and to assess things like conversational skills in simulation. So the modularity of this approach, where you've got this general information processing framework, then you need to specify an MDP for your particular domain, can work pretty well across some pretty disparate domains. Now, one of our goals with making these fine-grained inferences was to be able to build systems that could really respond to students. So we wanted to move beyond storing and processing data to try to think about how can we provide experiences to students based on our inferences about their understanding. And so I want to tell you a little bit about how we did that for equation solving. We developed some feedback activities. These were not the perfect feedback activities, but were intended to sort of test specifically how good is it to target activities based on inferences about what the student understands and what she misunderstands. So they were pretty similar across different dimensions of theta. That's what we'll be targeting. But they varied in terms of the specific content, which of those dimensions we were talking about. We conducted a lab experiment in which we recruited participants from Amazon's Mechanical Turk for a 3-day experiment. So on the first day, they solved problems on our website and completed a multiple choice test to get an assessment of their understanding of algebra. On the second day, they completed a feedback activity. One condition completed a feedback activity for a random skill, one of those dimensions of theta, but chosen randomly, not based on our system's inferences about their understanding. The other condition completed a feedback activity that was about the skill that our system believed they were least proficient at based on their problem solving on day 1. In session 3, we then again assessed their algebraic equation solving performance to try to see how it changed from session 1 to session 3. So we first looked just those two conditions, did they differ in how much they improved from session 1 to session 3? And what we found is that they did improve reliably, but there was no difference in the amount of improvement across conditions. So first that suggests, oh, targeting isn't really helpful. Looking a little bit more closely, we realized that there were some people for whom our targeting might not really be helpful. That is, those who either were near ceiling or close to mastery for all of the skills, all those dimensions of theta, or those who were struggling with all of them. Providing one skill at random might be just as good or almost as good as targeting it. So we looked a little bit more closely at those who had some skills that were mastered, as higher proficiency above 0.85 in our system, but we've checked for robustness along various sort of moving that around, so it's not just a specific cutoff. And we excluded from this participants who were below mastery in all the skills. What we see when we do that, when we just have participants who have varying skill levels, is there's a reliable difference in the amount of improvement by condition. So this suggests that there might be something there to be able to really target feedback, to choose feedback that's most appropriate for individual students based on inferences about their performance across a relatively complex task and lots of data collected about a variety of different dimensions. So I think there's more to do here to think about this adaptive feedback, what's the best way to use it, and so on, but it's kind of some encouraging first results. I want to turn now to thinking about kind of leveraging the modularity of inverse planning and what have we gained by having this generative model of actions. So we saw that we could use inverse planning for other domains. I told you about some work that collaborators as well as groups not related to us have done. But we also have kind of developed a general framework for adapting production rule models, which are very common for different educational domains, into this inverse planning framework so that we can try to infer which rule models are, which production rules might be being used most often, or which of multiple possibilities for misunderstandings might be really being used. We use that to model some data from Braithwaite et al. 2017. Some other ways that we've used inverse planning are to think about designing informative assessments and to infer student goals and rewards rather than just misunderstandings. And I'll tell you briefly about those last 2 points. So our work on designing informative assessments is really based on the same ideas from optimal experiment design and adaptive testing, where if you had a choice, if you could get one of these two distributions about your estimate of theta, you'd wish you could get the one on the right after a student completes the assessment. It's more concentrated. We've gained more information, even though the means are in exactly the same place. So adaptive testing often optimizes the test form or what a question is asked next to try to gain as much information as possible. We did the same thing with game design and inverse planning. So we considered varying lots of parameters of a game, like the incentive structure, where particular things were in the environment and which particular things were where. And we used this to infer, again, a posterior distribution over some theta about understanding our goals, where we're looking at the actions the player takes and the particular design of the game. So if we imagine that we can vary that, then we can try to estimate the utility of a particular game design. We'll estimate that utility as the expected change in information, which means that we need to be able to predict how much information we'll gain about understanding about that theta before we run the game. And here's where we use our generative model. We can sample possible understandings, we can simulate action vectors because we have this generative model, and then we can use MCMC sampling to try to infer that posterior distribution. That allows us to take a space of possible designs, combine it with this utility function, and actually do a stochastic search to try to choose a better game design. We compared this in an experiment with some lab participants. We were looking at estimating something about the ease of learning different categories, and we found that we got an information gain of twice as much from running an optimized game versus a random game. If we were thinking about with students, we might expect that with half as many problems, we could get the same information. So we could shorten our assessments just as we might try to do with some optimal experiment design approaches. We also in this looked at incorporating people's desires to understand the game. We saw there were some systematic ways in which people seemed to vary from what we expected. They might take actions that seemed like they had really possibly terrible consequences under the reward structure for the game, but they were systematically doing them. And we realized that we could try to think about what people might want to know about the game in the reward structure. And so we incorporated information gain that people might get by taking different actions. So they might not care about maximizing their points as much as they care about really understanding how the game works. We found that when we incorporated that, we significantly improved the correlation between the expected information gain from our estimates and the actual information gain when we had people play those games. So we thought this was kind of a cool application for really understanding what people might be trying to do in their actions that might be about more than simply what the game designers have built in, and that we can learn that by looking at the data. So to conclude, I've told you about inverse planning and how it offers a way to make sense of step-by-step data without intervening during the activity. One of the advantages, I think, is that we separate the details of the domain from the more general method for processing behaviors, and that allows us to apply this to a diverse set of educational domains and to adapt existing models of learning. There's a lot of interesting future work that I'd love to talk with you all about. We're looking at some things like how to automatically identify people who are poorly modeled, using search to try to improve the representation of a particular domain, and trying to think about how do we present these results to teachers as effectively as possible so that they can use the results of systems like this one. So I want to thank all of you for your attention. Thank my collaborators, especially Tom Griffiths, who was a collaborator on all of this work, Rachel Jansen, who was a collaborator on the equation solving work, Matej Zaharia, who was a collaborator on the game design work. So thank you so much.